Lesson is about derivatives of a function. It's whether, and so that's called differentiating a function. And what if the lesson is for you to decide whether you can differentiate a function or you can't. There are some functions that you can't take the derivative of. There are some functions that you can't take the derivative of them at a specific point. Okay? And that's what we're going to talk about today. So we're going to define the derivative of a function, graph the derivative of a function, identify where a function has no derivative. So we have this one and this one. So here's where it shows you the two separate ones. Previous to today's little thing where you were freaking out. Okay, so here's your two separate limits that you could use. Okay, we've used this one the whole time as f approaches c, where we plug c in for x, or f approaches x, right? And we use the limit as h approaches 0. The other method you could use is you could go right ahead and make it approach c right off the hop. So you would do f of x minus f of c all over x minus c. And what this does is it just literally takes out all of the h's and it replaces them. So it inserts the c in right on the bat. So this one here, what we'd actually have to do is we have to find the limit and then we'd have to fill in our value, right? These two are interchangeable. They can give either one. Tell you which one I use. None of them. I just use the derivative rules after this. So I only use these if forced to. So AP questions sometimes force you like that one did. Number 3 forced you to use these. But if they just ask me to find the derivative and they just let me find the derivative however I want, I will never choose this option because it's way longer than anything else. Okay? And we'll see that in the next example. So example 1 here, finding the derivative of a function at a number c. I'll do the 3 different ways. So I'm going to do the top one. Actually, I'll do the bottom one first because it's one we're most used to. I'll do the top one and then we'll actually just do the power rule. Right? Okay. Or just do the power rule, but we're not going to do that, even though that's where my heart wants to go. Okay. I might just do the top one first, because everyone can do the bottom one. I'm just going to show you the top one because it's just a little different. Okay? And then we'll do power rule, because that's where everyone wants to go. So, on my notes package, which I still haven't uploaded for some unknown reason. I guess you're writing it, so it doesn't really matter. But in there, it shows the limit as h approaches 0. Okay. So we're going to do the first one. So we're going to write it down. We're going to go f prime of c, because it wants it at any real number c. So f prime of c equals the limit as x approaches c. And why is it x approaches c? Because I have an x minus c in the denominator. If I plug in c, I got problems, right? And then I have f of x minus f of c. So the first thing I'm going to have to do is find f of c, which is literally just this with a c in it, and then f of x. So I'm going to go the limit. Both of these equations have their pros and cons. The one that we've been using's con is that you have to expand a whole bunch of x plus h's out, right? This one's con is you often have to factor to get rid of the problem. So you either front end load a whole bunch of work or back end load a whole bunch of work, but it's the same deal. It's also kind of really ugly when it's radicals and rationals using this one. Because you're going to have to try and factor rationals. So we go f of x, which is x squared minus 5x. This one is equally as easy to use as the other one when it's a polynomial. But this one, when you have to do rationals or radicals, gets real ugly because you have to try and get this factor to go away. So you're factoring something with rationals and radicals. And you often cry if that happens. So polynomial, use this one. So we have x squared minus 5x. And then we have minus c squared minus 5c over x minus c. It has to stay here. That's why that example on the other one where they did it this way, that's why the example, if you looked at number 1, it was on the second sheet, when he filled in the 2, he stopped here because you can't go any further. Unless you know what C is, 2, 7, whatever, you're stuck. And we're done. Yeah. Plus 5? Yeah. But you're stuck until you know what C is. So C is 2, you plug it in. C is 3, you plug it in. And then you would have to factor cancel off the x minus 3, 2, whatever, and then you can keep going. This one, that's as good as it gets with C. Okay? All right, power rule. So we're going to do f prime of x first. So what do? We take the 2, we drop it in front. It becomes 2x to the 1. It drops down by 1. And then anything with just an x becomes minus 5, because this would be x to the 1. The 1 would join the 5, so I get negative 5, and the x would go to a 0, which would cancel. Okay, we want f prime of c. 2c minus 5, done. I like that one too. I like the one as h approaches 0 better, because h approaches 0 one will actually get you that answer. It'll get you 2c minus 5. It'll get you the same thing. This one does not.
And it'd still be right.
Yeah.
So those are still equivalent?
Yeah. This one you would just need like a 3 or a 2 or whatever, plug it in for those, right? Then you'll get a number back here, then you'd factor it to get, and you'd have a number here, and then they would cancel off, and then you would get the same answer in the end. Hence why I waited till this very moment to show it to you. Okay. Yeah.
Is there a reason you would do it like that?
Because they ask for it. Only because the question is like number 3. Number 3 made you do it this way. That's the only way I would ever choose that route. But it sometimes is faster too. If someone's really bad at like expanding binomials or something like that, this one doesn't make you expand binomials. And if you have a 2 or a 3, you can plug it in, and all you have to do is factor, and it cancels, and boom, you have an answer. So ultimately, if it wasn't a C, if it was like a 2 or a 4, this one sometimes is nicer. As a C, it does not look nice. Okay, so then there's this one. Okay. If f has a derivative, the f is said to be differentiable. So a plain old polynomial, boom, 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 every polynomial will be differentiable because it needs to be continuous in order to be differentiable, and it needs to not have certain other things happening. Which the certain other things that happen when you have one-sided limits.
So it would need to like have a limit because it would need a limit to be continuous.
Right. So yes. So in order to prove that something's differentiable, it has to be continuous, and it has to not have a cusp or an asymptote, which we'll talk about in a second. And that only happens when you have one-sided limits. A cusp is when, like, from one side limit, it comes down like this, and the other one comes down like this, and it makes a point. That's a cusp. At that cusp, it's not differentiable. Because you get a vertical asymptote, and a vertical asymptote is divided by 0. Doesn't exist. So once again, if you have a vertical asymptote there, the graph is not continuous there, you can't have it. So there's 2 things. So we're going to differentiate f of x equals root x and determine the domain of f prime of x. Okay? So the first thing, let's sketch it. So we have 0, 0, 1, 1, then 4, 2. And it looks like that. So what's our domain?
X is
Greater than or equal to 0. That's the domain of f of x. Remember that my microphone picks up everything you say. I'm not even joking. It legitimately does. So, yes. I sound extremely loud. You just sound sort of loud. Picks up everything. It's a conference mic. That's on you, I guess. But no, 2 times speed people listen to me at that, and so it's fine. They do.
That's how I listen to all my cars.
Okay, so if I want to find the derivative of this, I can use the limit as h approaches 0 formula, right? And find it out that way. So I'm going to show you. We have f of x equals root x. F of, you guys, the talking is getting really annoying. Please stop. This is going to be x plus h. So we want to find f prime of x. Equals the limit as h goes to 0 of f of x plus h minus f of x all over h. And what do I have to do when I have radicals? Multiply the conjugate, and do not put together the two terms that are not conjugates. Why? Because that h needs to go away because the h is my problem. Distribute it in, you can't get rid of the problem. So I'm going to multiply by root x plus h plus root x. And then I'm going to do it to the bottom, but I'm not going to distribute it. I'm just going to leave them separate factors. I'm going to have the limit as h approaches 0. Root x plus h times root x plus h is x plus h. Then I get minus root x times x plus h plus root x times x plus h cancels. And then minus root x times root x is minus x all over h root x plus h plus root x. The x's cancel, the h actually cancels, and I'm left with 1 over. Now my h problem's gone, so I can plug in. When I plug in, my limit goes away. So I get root x plus 0 plus root x, and then I get 1 over 2 root x. Which seems actually quite complicated. Now, also, they wanted the domain of f prime of x. What's the domain of that? People will tell me it's x is greater than or equal to 0, because that's what it was before. My x is in the denominator, so can it equal 0? No. So what's actually the domain of f prime of x? X is greater than 0. Just so you know, whenever you have a one-sided graph like this and it just stops, this piece right here, the very bitter starting edge, you can't find the derivative of it. Why? Because it'll always slam it into the denominator. So that part can't exist in the domain. Okay? Now, let's do this with power rule. It doesn't look like a polynomial, but it is just an x to a root. And so then I told you guys that in calculus, we're going to be switching all of our radicals to fractional exponents. I said this in 30-1 and said, good practice to do it now. So what is root x the same as? X to the 1/2. So if I just have a variable to an exponent, I can do power rule. Whether it's a 2, a 4, a half, 3.5. As long as your exponent is a number. If it's like x to the x, or x to the c, or something like that, you can't use power rule. You can only use power rule when you have a variable to a numerical exponent. It can be a negative exponent, it can be a positive exponent. So what do I do when I do power rule? The half drops in front, so I go f prime of x equals, half joins the 1 in front, so I get 1/2, x, and then the half drops by 1, so I get negative 1/2, because a half minus 1 is just negative 1/2. Now, how is that the same as that? They have to be the same, they're both derivatives. What can I do with the negative exponent?
You can flip it.
You can move it to the bottom and then it'll become a positive exponent because it's technically over 1, right? So I get 1/2 times 1 over x to the half if I want to write it separately like this. Or I can say, hey, it just joins the denominator. And then x to the half is just root x. Matches the same answer. The thing with the limit formula is it'll always have the root on the bottom and all figured out for you, and the roots don't go away, so you have to change fractions to roots. But that's only positive. Yeah. Because you have to take this exponent and subtract 1 from it, right? If it was a 2, it became a 1. If it was a 4, it became a 3. If it's a half, when you subtract 1, you get negative 1/2.
Oh, okay.
You always bring the number, drop it in front, reduce the exponent by 1. So then there's this problem. Then we have, when it's not differentiable. Okay, so when a function doesn't have a derivative, the first thing you have to cover to say, yes, it could possibly have a derivative, is the function has to be continuous. Continue. Ooh, wow. Looks so weird when it's all capitalized. On the x dot, I keep going, I guess, in capitals. Oh, we're down slow. Okay, so it has to be continuous on the x value. So even if the graph is continuous everywhere else, but I'm finding it at like 2, it's not continuous, it's done. You can't find the derivative there. So even before these other rules after, like if this happens or this happens or this happens, it's not continuous. Even before that even happens, if the graph is not differentiable, sorry, if the graph is not continuous there, it's done. I don't even need to look at what the graph looks like. So there are other reasons. I bulleted them. You can write a 1 beside, a 2, and a 3 if you'd really like to. It doesn't matter. So suppose a function is continuous. See? Right there. It has to be continuous before I even go to these 3 bullets. Do you see that? If the function's not continuous, it's done. I don't even really care. It's not differentiable. So the key thing is it has to be continuous to be differentiable. This is what they do in AP. They go, if it's continuous, then it's differentiable. Well, possibly, right? Does a graph have to be continuous to possibly be differentiable? Yes. If it's differentiable, does it mean it's continuous?
No.
Always. In order for something to be differentiable, the graph has to be continuous. They'll use these interchangeably. So we're going to think about it. Okay? If a graph is continuous, is it differentiable?
Yeah.
Maybe. If a graph is, you're going to see why. Boom, boom, boom. There's bullets right here. You're going to see why. If a graph is continuous, is it differentiable? Maybe. If a graph is differentiable, was it continuous? Absolutely. So they'll say they use the always or sometimes, or they'll use must be true. They use that. What must be true? Well, if it's differentiable, it must be continuous. That must be true. If it's continuous, it must be differentiable. That is not true. Yeah.
Are we saying like continuous in regards to one point because you can have like parts that are continuous and other parts that
Continuous at a point.
Okay, so it'll specify at
Mhm.
that point. Okay, yeah, that makes sense. I thought you meant like the entire graph. I was like, not necessarily.
Well, even if a graph is continuous, the entire graph, it doesn't mean it's differentiable. And we'll see why. So differentiable means it has to be continuous, but continuous doesn't mean it has to be differentiable. They ask them backwards like that all the time with must. Must be. Must be happens too much in AP. So we're going to look here. So the limit as x approaches c from the left of f of x minus f of c of x minus c exists, and the limit from the right exists, but they're not equal.
No,
It's immediately not differentiable because the graph is not what?
continuous.
Continuous. So that would be like this. That would be not continuous. So not differentiable. Another way it is continuous but not differentiable. It's, for example, the absolute value graph. This is just another example. So if we look at the absolute value graph is 0, 0, and then negative 1, 1, negative 1, 1, 1, 1, 2, and 2, negative 2, and 2, because all your y's are becoming positives. So it looks like this. We agree? Is that a continuous function? Yes. If I go to draw the tangent slope. The tangent slope is what? A fancy way of saying making you find the what? The first derivative. We agree? If I draw the tangent slope of these lines, when people ask you for tangent slopes of these, they're easy. It's whatever the heck the line slope is. These ones are the easy ones. You had a question like this on an AP question in the homework. So if they ask you for the tangent slope of a line, you just find it. Okay? So those ones are the easy ones. Tangent slopes of curves are a little more difficult because you have to figure out what the heck it is on that curve, right? But a tangent line of a straight line is the line slope. Done. So if they ask you the tangent line of that. The tangent line of a point will be a vertical tangent line. The only way I can draw a tangent line of this point is to actually go this way. Of a point. If it's rounded, it'll be horizontal, but of a point, your tangent slope is vertical. What is the slope of a vertical line?
Y or x equals
No, you
A
can't.
vertical line, x equals, or x can't equal something.
When I used to teach grade 10, and I talked about vertical lines, and I talked about skiers. In grade 10, I would have a skier, and the skier would be on this type of line. That's a horizontal line with a slope of nothing. They're going nowhere. We agree? Okay. Then I had the skier, and he came along, and his life got substantially worse. So I give him a little thing. He fell off. He's not peeing. He fell off the vertical line. Good, it still makes jokes. Y'all still laughed. I used to do that. I haven't taught since 2010, but they laughed then too. Good. Okay, so vertical line. He jumps off of there. This is like hundreds and thousands of millions of feet.
How fast the feather was falling. Yeah.
It'll take him years.
He's falling very fast. He becomes undefined, is what happens to him.
It's hard to find.
No, he's not hard to find. He's undefined. He's also dead. So, his slope is undefined. Vertical lines are undefined because they can be any number. Their slope is any number over 0. What does that mean? Okay, let's go like this. People are like, how's that happening? This could be like 1 over none. 5 over none. 1 million bajillion over none. So that's why your undefined slope is always over 0, right? It's a vertical slope. It's undefined. It can't exist because your denominator is 0. We agree? Can we find the derivative of something that doesn't exist? No. So whenever you get a vertical tangent slope, you can't differentiate it. So where on this graph can't I differentiate? Yeah, at the 0, 0. That's the only place. You could differentiate this arm and you could differentiate that arm if they were piecewise functions. You just can't differentiate at 0, 0. So if I asked you to find f prime of 0, you'd say? Does not exist. I gotta write that. So wherever you have a point, it's done. So this is where I said to you, if a function is continuous, does that mean it's for sure differentiable? Must it be differentiable? No, this one's continuous, but it's not differentiable at 0 because there's a point. Okay? So we have to it has to follow 2 rules in order to be differentiable. It has to be continuous, that's true, but then it also has to follow the rules of it can't have a vertical tangent slope, right? And that's it, basically. Yeah, it's a vertical tangent slope. This little red one that's running through here, that's a vertical tangent slope. See, that's why I drew the guy dying and undefined.
He'll be fine.
Shake it off. Dust them off and stand them up. Okay.
Put a powder.
So this one here, it says the one-sided limits are both infinite and both equal to negative or infinity or negative infinity. For example, cube root. So we did like a square root already. A square root looks like this. And we know that it's not differentiable at 0 because that throws the denominator into the 0 and that one's gone. Also, it's not differentiable there because what type of tangent slope am I going to get on this bad boy? A death one. Yes. Don't write that on the AP exam. They will not know what you mean. A vertical. Okay. Cubic functions don't just start and then go right, or don't just start and go left, because I can take cubic negative cube roots, right? I can only take positive square roots, so that's why it starts with 0 and goes onwards. These, when you take cube roots of positive numbers, you get positive numbers. So it goes like this, right? And then when you take cube roots of negative numbers, they're just negative y values. So it just literally reflects itself. So you get a graph like that. So when you get a point, it's not differentiable. We agree? When you get a point of inflection, you're going to get a vertical tangent right here. Because that's the only way I can draw that tangent line to it, is to draw it vertically, or else it's going to cross through somewhere else. Right? So this here would be f prime of 0 would be what? Does not exist. Is my graph continuous?
Yeah.
Yes. However, it's not differentiable. And they'll be like, the graph above is differentiable, continuous, continuous, not differentiable, not continuous, differentiable, not continuous, and not differentiable. Not continuous and differentiable will never happen. Please never circle that one, because it has to be continuous in order for it to be differentiable, and then also follow the other rest of this crap. Okay? So the not continuous and differentiable can't happen. Just like, not that answer. Slice through it. Anyhow. This one. Both one-sided limits are infinite, but one equals negative infinity, the other one equals positive infinity. When this happens, the graph of f has its vertical tangent at the point, and the point is referred to as a cusp. Here's your cusp word, Shane. The cusp. Not a cusp. A cusp. So, let's sketch this one quickly. So this one looks like, it looks like this. So a point they refer to as a cusp. So this here, once again, is a point. Just like the absolute value graph had a point. They call it a cusp. So this would be f prime of x. Oh, f prime of 0, I meant to say, does not exist. Now some people will say, well, what happens if there is an actual vertical asymptote in the graph? The original graph. Then your graph's not continuous, therefore it's not differentiable there, because it can't be differentiable where it's not continuous, right? Wherever it's not continuous, that immediately makes it not differentiable there. I don't even care about cusps, I don't care about points, I don't care about curves, I don't care about vertical asymptotes. The moment that the graph is not continuous there, it can't be differentiable. So last piece. This is called, given this piecewise function, why is there no derivative here? So let's look at it. The best way to do it is to actually sketch it. So I'm going to start at ones. So when I plug in a 1 on the left, which would give me my left limit, I should put it in work, I got 2. So when I plugged in 1, here I got 2. And then I want to plug in 0, I'm going to get 4. And then when I plug in negative 1, I get, I'm going to show it, f of negative 1, I have to plug it into here. I'm going to get 2, right?
I think you get 2 wrong. Oh, wait.
Graph.
Could be.
It's just a concave down parabola. Now, if this graph kept like going in some way that was like a nice little curve and out this way or something, golden. We get a cusp, a point, something like that, we're done, right? So let's fill this one in. If I do f of 1 into this one, I get 1 squared plus 1, which is still 2. That's the limit from the left, or from the right. So it's still here, closed dot. So that's good. That means it's continuous at the very least, right? That covers first checkbox. Now let's fill in f of 2. We get 2 squared plus 1, which is 5.
Why are we doing 2 all of a sudden?
We need the right-hand side of the graph. Then we pick 3, we can pick 4, pick 5. I'm just picking points and drawing graphs. Anything greater than 1 follows this graph.
Yeah.
So I picked 1 and I got 1 point. Now I have to pick 2 to get another y value so I can keep sketching it. Yeah. What happened here, people? What's this? A cusp. So f prime of 1, does it exist? No, f prime of 1 does not exist. And if they wanted you to explain why, because there is a cusp. Yep. It's the accurate word for that, a pointy bit.
Is it downwards? Or can it be upwards?
Could be a pointy bit whichever way. Because there's a cusp at x equals 1. Now, sometimes they'll just give you this question, and then they'll do the whole A, B, C, D part, like I told you. This graph is continuous and differentiable. Continuous and not differentiable. Not continuous and differentiable. Not continuous and not differentiable. Not continuous, not differentiable can work, right? That can be true. What is this graph?
Continuous.
Continuous, but not differentiable. Do you see how they can ask that question? Yeah?
Wait, so why though didn't we do it like how you would do limits before, where you would like, because you know how it'd be like, oh, if you're looking for one from the right, you would plug it into the one where it's like greater than or equal to one, and then usually if you're coming from the left, you would do.
That's if you want to show limits, which I did show limits in the actual notes, but you don't have to show limits if you're just figuring out if this exists or not. You have to do two things. You have to show it's continuous, which I did by actually graphing it. And by graphing it, I literally plugged in 1, and then put that dot, and then plugged in a whole bunch of, well, a whole bunch, 2 more values less than 1, so 0 and -1. Then I sketched the right-hand side by plugging in 1, and then I plugged in one more value greater than 1, which was 2, and then I already saw there was a cusp and it was done.
Okay, should we ever just put in a calculator about booty?
You could if this was a calculator section of your AP section. And then what you would do is you plug them both in, you'd go look at one and see if it's doing some sort of point cusp thing. Point to bit. Proper terminology. So this just is a little summary. It says, theorem, if a function f has a derivative at a number c, then f is continuous, right? So if you can differentiate it, if there's a derivative, we know for sure it has to be continuous, okay? Corollary means same thing said differently. If a function f is discontinuous in a number c, then there is no derivative, right? If it's discontinuous, no derivative. It immediately kicked out, right? Then here it shows some information. So here it says f is continuous at 1 and f prime of 1 exists because there's no cusp and it's continuous. We agree? This one, g is continuous, true, but it doesn't exist for the derivative because there's a pointy bit. This one, h is discontinuous, and because it's discontinuous immediately, h prime does not exist. So one of those where it's like not continuous and the derivative doesn't exist is when you just look at a graph and it's not continuous. Boom, pick that one, right? And then here it just shows, I just want to show you the heave side function, it's just what it's called. It has a derivative at x equals 0. But if you go to draw this one, it doesn't actually exist. So they want you to determine if it has a derivative. Well, let's check it out. This one on the left of 0 has a line at y equals 0. I'm going to use a different color. You aren't going to see it. And it's not equal to. Open dot, boom. Just through the left-handed side, correct? That's this one. This one is equal to, but it makes the line y equals 1. Done. Is there a derivative at 0? No. At 0, 1.